Okay, so this is sample problem 3302. So it says the figure shows a system of 3 polarizing sheets. So 1, 2, 3 in the path of the initially unpolarized light. So the polarizing direction of the first filter is parallel to the y-axis. So the light is coming from the top right and then to the bottom left. So this one is parallel to the y-axis, and that the second sheet is at the angle of a 60-degree counterclockwise from the y-axis. So this one is 60 degree, and then the third sheet is parallel to the x-axis. So this is horizontal, this is vertical. And what fraction of the initial intensity I0 of the light emerges from the sheet 3-sheet system, and in which direction is that emerging light polarizing? Okay, so just as what we saw on the video, if we don't have the middle one, then it will be totally dark. The intensity will be 0. But after inserting a polarizing filter with an acute angle between the first and third one, then there will be some light can go through this 3-sheet system. Okay, so yeah, so before sheet 1, so this is 1, this is 2, this is 3. Okay, before sheet 1, the light is unpolarized. So we can we have the intensity I0, and then we can denote it as this one. So we have a vertical and horizontal component for the E field of the light. Okay, so after going through sheet number 1, okay, it become polarized. And as much as this is vertical, so it becomes vertically polarized. And I1, we will say this is I1. This is I1. I1 becomes half of I0. So as we have the equation in the previous page. Okay, so, or you can say in y-axis. Okay, so after sheet number 2, it is of course polarized. Okay, so the intensity of I2 is here. So I2 will be I1 times cosine of 60 degree and then quantity square. Because yeah, here it is vertically polarized, which means that there is a 60 degree between the incident light polarized angle and the polarizing filter. Okay, so we have a I1 times cosine square of a 60 degree. Okay, and cosine square of 60 degree is 1/2. So this is half of I0. This is I1, and then half, and then quantity square. So we have I0 over 8 for I2, and then after sheet 3, so of course it is still and actually this is polarizing like this. This is 60 degree, so this is 60 degree counterclockwise. From y-axis, so So this is the polarizing angle. Okay, so after sheet number 3, it is of course polarized. And I3 will be I2 times cosine square of theta. Okay, so actually the incident line is 60 degree to the y-axis, and then it is parallel to x-axis. So the angle between them is 30 degree. So we have a cosine square of 30 degree. Okay, so this is 1/8 of I0. This is I2, and then cosine of 30 degree is square root of 3/2, and then quantity square. So the answer will be 0.094 I0. Okay, and the angle will be parallel to x-axis. 0.094, roughly around more than 9%. Roughly more than 9%. Okay. So next we talk about some property about the light. So I suppose you should have learned it in high school physics, which is about the optic stuff, the reflection and refraction. Okay, so reflection is 反射, refraction is 折射. Okay, so you can see here. So here is the light, and then this is air, this is water. I suppose it's water, or maybe some water with something else. So you can see the refraction here, and actually there's also reflection. So this is the law of reflection, which means that the angle of reflection equal to the angle of incidence, both relative to the normal. So theta 1 prime equals to theta 1, which is quite trivial. So this is the boundary of the two material, and we can draw the normal line. And then the incident angle is from the normal line to the incident ray. So this is theta 1. So when we talk about the reflection, so this is the reflection ray. So this is theta 1 pi, also counting from normal line to the refracted ray. So we have theta 1 equals theta 1 prime. Okay, so for this system, part of the light will be reflected, part of the ray will go through, but with refracted angle. Okay, so in general physics, we don't need to consider how much percentage is refracted, how much percentage is refracted. Okay, but yeah, maybe in EM theory, we need to write something called TEM wave, but it will be quite tedious to write those stuff. So you only need to know a part of the wave is reflected, and then the remaining is refracted. Okay, and the refracted angle is equal to the incident angle. That's the law of reflection. And for the law of refraction, it is called the Snell's law, and then it is actually n1 sine of theta 1 equals n2 sine of theta 2. n1 and n2 are called the index of refraction, which is related to the material itself. So for air or vacuum, the n1, the index of refraction is 1, and for all the other material, the n will be a number larger than 1. strictly larger than 1. And actually this number is related to the speed of light in that material. For example, if we consider V of the material, for example, this is water. Just say the velocity of light in the water is Vm, then or maybe we can say Vw. Vw is the velocity in the water, and then c is the speed of light. Vw. Okay, so and the index of refraction of the water is defined like this. So c over Vw is Nw. Speed of light is the ultimate speed. No speed can ever larger than the speed of light. So Nw should be larger than 1. So unless the speed of light in the air or vacuum, the n is 1. All the other material is strictly larger than 1. Okay, so here we talk about the N1, N2, which means the index of refraction in the material 1 and material 2. And the theta 1 is also counting from the normal line to the incident ray, and then the refracted angle theta 2 is also counting from the normal line to the refracted way, so theta 2. Okay, so in this case, the material 1 is air, and then material 2 is water. So in this case, N1 is smaller than N2. And in that case, sine of theta, when theta is between 0 and 90 degree, sine is a increasing function, which means that theta 1 will be larger than theta 2, as much as N1 is smaller than N2. Okay, so you can see N1 is larger than N2. And vice versa. If N1 is smaller than N2, then theta 1 will be no. I mean, if N1 is larger than N2, then theta 1 will be smaller than theta 2. Okay. Okay, so this slide also talk about the chromatic dispersion. Dispersion in Chinese, it is called 色散. Okay, 色散. Okay, chromatic dispersion of white light. So white light include the different spectrum of the light, of the visible light. So the blue component is bent more than the red component. Okay, bent more than the red component. So you can see, if for this case, the white light is from the air to the glass. Okay, so you can see. If we try to extend the incident ray like this, just imagine there is no water, no glass there. Then the light can go straight to this way. But here we have glasses, so there will be refraction. So in this case, it tells you that the red light can bend less. So it talks about this angle and this angle. So this angle is smaller than this one, which means that the blue component bent more. Okay, so this is the other case if the incident light is from the glass to the air. Okay, so in this case, this is how the red light bend, and then this is how the blue light bend. So you can also see that the blue light bend more than the red component. Okay, so passing from the RL to yeah. Okay, so that's why we use the red light for the traffic light, because the red light can suffer from a less bending due to the refraction. For example, if it is raining or it is foggy, then probably the green light may be refract, so we may not be able to see it from far away. But the red light can have a better capability to go through the rain or the fog. And we also talk about the total internal refraction. I suppose you should have also learned it before. So just as what I mentioned, if theta, if n1 is larger than n2, then theta 1 is should be smaller than theta 2. So, but actually theta 2 can be as large as 90 degrees. It cannot be larger than 90 degrees. So if theta 1 is large enough, and then you plug in this equation, then there might be some problem. Just say, now we have a n1 sine of theta 1 equals n2 sine of theta 2. Now we suppose n1 is larger than n2, and then we would like to find sine of theta 2 equals sine of theta 1, and then times n1 over n2. And here we assume n1 is larger than n2, which means that n1 over n2 is larger than 1, because they are positive number. Okay, so here this one is larger than 1, which means that this is strictly larger than sine of theta 1. Oh, this is not a good way, but at least you know this one is larger than 1. If sine of theta 1 is large enough, this number may be larger than 1. Maybe larger than 1. And you know sine is a function between -1 and 1. So if sine of theta 2 is larger than 1, there should be no solution. There should be no solution in real domain, in real number. So in that case, there will be so-called the total internal refraction, 全反射. Okay, so you can see here. So this is the light source. If it is 0 degree, it is going through, and then if it is, some of it is also refracted, and then the incident angle become larger. So part of it is refracted and part of it is reflected again. And then at this point, the refracted light is actually 90 degrees. It's actually 90 degrees, so it is actually touching the boundary of the two materials. So, and actually we call this angle theta c to be the critical angle, theta c. So if the incident angle is even larger than theta c, then all the light will be refracted, because you cannot find a way that sine of theta 2 is larger than 1. So there will be no answer. Then all the light is refracted, and we call it the total internal refraction. Okay, yeah. So this is the and actually this one is more advanced. It's more advanced. It's called the frustrated total internal refraction. I don't know if it has a Chinese name, but if it don't, then it's probably called 沮丧的全反射，沮丧的全反射 because so here just imagine this is a stream, okay, with 45-90 degree. So if actually we have two streams, and then if they are placing far away enough, then the incident line is totally internal refracted. It's totally internal refracted. Okay, so suppose that the index of refraction is large enough so that even for 45-degree input angle, then incident angle, then all the light is refracted. And then, so let's go to this one first. If these two streams are touching each other, there is no gap in between, then this boundary does not exist anymore. So all the light can go through. So in the middle one, it is the frustrated total internal refraction, which is the interesting case. So actually, if you have interest, you can try to check it out in this link. And actually, the frustrated total internal refraction is like if you place these two streams close, but with a small gap, then it will not have a total internal refraction anymore. Part of it can go through, and part of it is reflected. Okay, so this phenomenon is quite interesting, and actually it is related to the quantum theory. And actually, we don't have enough time to talk about the tunneling effect. Tunneling effect in chapter 38. But if you have interest, you can just check it on the UM Moodle. I have posted the link from the last semester. Okay, so you can, it is actually related to the solution to the Schrödinger's equation. But this phenomenon is quite similar to the tunneling effect. The tunneling effect is like so probably in classical mechanics, if you have a potential wall, then if it is an object, if your object needs to go through the wall, then it should have sufficient kinetic energy to transfer to the potential energy. Suppose this is a potential wall. Just like if it is a wall, then if you need to throw a ball over the wall, then you should provide sufficient kinetic energy so that the kinetic energy of the ball can transfer to potential energy and then get over the wall, and then it can go through. Suppose the K is large enough. But if the K is not large enough, then you probably throw the ball up to here and then it will bounce back. But for quantum theory, if the kinetic energy is not really large enough, it can still have some probability that the object can go through. Or the light, or maybe a particle can go through. And here, suppose you have a light, so there will be some probability that the light can go through this gap. This gap is like the potential wall, because if this gap is sufficiently large, then it is like this. The gap is and all the way cannot go through, and then all the way will be totally internal refracted. But if this gap is small, is zero, then all the way can go through. But if this gap is small enough, then there will be some probability that the part of the wave can go through, and part of the ray is refracted. So this is called the tunneling effect in quantum theory, and this is similar to that. Okay, so yeah, so this is a table related, summarize the indexes of refraction for different material. So for vacuum, it is exactly 1. For air, even though it's not exactly 1, but it is quite close, it is only 1.00029. So we usually regard it as 1. And if it is water, it is roughly 4/3. And then yeah, sodium chloride, yeah, 1.5. And then yeah, and then glass, typical chrome glass, 1.5. Sugar solution, or also 1.49. And this one, ladies like, what ladies like is a diamond. So the indexes of refraction is 2.42. So you can see the chromatic dispersion due to the diamond. And as much as the index of refraction is large, this chromatic dispersion will be stronger. Okay, so here we also talk about the polarization by refraction. Okay, so suppose we have the incident light which is unpolarized, and then suppose we have two material, material 1 and material 2, and yeah, so actually there is an angle called the Brewster angle, theta b. If the incident angle is theta b, which is given as n2/n1, and then take the arctangent. So this is a specific angle. If the incident angle is actually this Brewster angle, then the reflected light will be totally polarized. And the refracted ray will be partially polarized, because some of the wave which is somehow like parallel to the plane. Is yeah, only this. Yeah, only the way with the parallel component can be refracted. So you can see here we have unpolarized light. So we have the component with indicated by the green arrow. We have also the perpendicular component indicated by the orange dot. So the orange dot can go to both paths, but for the green arrow, it can only be refracted. It cannot be reflected. So it means that the reflected wave is totally polarized, but the refracted wave is partially polarized. So at least the green arrow component is stronger than this one, because originally these two components are equally strong as each other. So for the refracted wave, the green arrow component is stronger than the orange dot component. Okay, so yeah. And this is the Brewster angle, and actually we can prove that theta b plus theta r should be 90 degree, which means that this is theta b, because the incident angle is theta b, and then the refracted angle is actually the incident angle. So this is theta b, this is theta r, which is the refracted angle. So theta b plus theta r is 90 degree, and then this is 180. So which means that this angle is also 90 degree. This angle is also 90 degree. Okay, we can try to simply prove this. Okay, so as much as we have n1 sine of theta 1 equals n2 sine of theta 2, and here we have theta 1 equals theta b equals arctangent of n2 over n1. And we would like to find of theta 2. What is theta 2? Theta 2 is the theta r. Theta 2 is theta r. Okay. So here, theta b is theta b. Theta b is n2 over n1 arctangent. So n2 over n1, this is theta b. So this line is a square root of n1 square plus n2 square. Okay, so okay, let me just put in the things. N1 sine of okay, we put in this one, n1 sine of theta b equals n2 sine of theta r, and then here we would like to find theta r equals n1 over n2 times sine of theta b. Okay, so from this figure we can see sine of theta b should be n2 over square root of n1 square plus n2 square. So we have n1 over n2 and then times n2 over square root of n1 square plus n2 square. Okay, so we can cancel n2 and n2. We have n1 over square root of n1 square plus n2 square. Okay, here we have n1 over this one, n1 over this one, which means that it should be like this one, or it is actually like cosine of theta b, cosine of theta b. Okay, so we have a sine of theta r equals cosine of theta b, and actually they are both acute angle, so we can write it as a sine of pi over 2 minus theta b, which means that we have a theta r equals pi over 2 minus theta b, so we have a theta b plus theta r equals pi over 2, or 90 degree. So we prove this one. Okay, I think last year I put it as a problem in the exam. But actually, as I remember, few of the students can prove it like this. They just try to plug in the numbers and then to show. Actually, for that problem, I still have given them input incident angle for how much degree, and then the refracted index is some number, and then I asked them on what is the angle of theta b plus theta r, or theta I plus theta r, when the refracted wave is polarized. But yeah, so many of them just plug in the number and then calculate the number. Also, they get maybe like 89.9999 something degree. Okay, so I think we finished all the material in chapter 33, and here is two sample problem, two additional example. Okay, so this one also related to the polarizing filter. So it says unpolarized light is sent into a system of three polarizing sheet. The angle theta 1, theta 2, theta 3 of the polarizing direction are measured counterclockwise from the positive direction of the y-axis. From the positive. So this is positive y-axis, and then we calculate from here. Here to here is theta 1, here to here is theta 2, here is theta 3. Okay, so yeah. Okay, so angle theta 1 and theta 3 are fixed. They do not change. They do not change. But angle theta 2 can be varied. Theta 2 can change. So the intensity of the light emerging from sheet 3 as a function of theta 2, the scale of the intensity axis is not indicated. So it does not tell you what is the maximum point. It just tells you that as I measure different theta 2 from 0 degree to 180 degree, and then we measure the intensity of the light, and then the shape is like this, like a shifted or a negative cosine or a sine square, something like sine square. Okay, so yeah, so what percentage of the light initially intensity is transmitted by the system when theta 2 is 30 degree? Okay, so here, first thing we need to determine the angle of theta 1 and theta 3. Theta 1 and theta 3. Okay, because it is a fixed number, but originally it does not tell you. So we need to get theta 1 and theta 3 from this figure. Okay, and as we see, I is 0 when theta 2 is 0 degree, 90 degree, and 180 degree. Okay, so I equals 0 at theta 2 equals 0 degree, 90 degree, and 180 degree. Which means that the angle between theta 1 and theta 2 should be 90 degree, or this one, theta 2 or theta 3 should be 90 degree to make the 0 point, the unity point, the 0 point here is at 0 degree, 90 degree, and 180 degree. So you can imagine at least one of it should be 90 degree. Should be 90 degree. Just say for example, theta 1 is 90 degrees. Suppose theta 1 is 90 degree. So theta 1 and theta 2, when theta 2 is 0 degree or 180 degree, there will be 90 degree between them. So there will be no light can go through theta 1 and theta 2. So if there's no light going through theta 1 and theta 2, there's still no light going through theta 3, the sheet 3. So at least one of the filter is 90 degree to the y-axis. And this is not enough because we need an additional 0 point at 90 degree. So probably there should be another filter just say theta 3 should be 0 degree, so that when theta 2 is 90 degree, there will be 90 degree between theta 2 and theta 3, and there is no line can go through. So which means that for theta 1 and theta 3, one of them should be 0 degree, one of it is 90 degree. But which one is 0 degree, which one is 90 degree is not really matter. The answer should be the same because the system is quite symmetric. So we will say without loss of generality, we assume we can take theta 1 to be 0 degree, theta 3 to be 90 degree. So if you don't believe, you can just repeat the forthcoming procedure by assuming theta 1 is 90 degree, theta 2 is 0 degree, then you should get the same answer. Okay, so here it actually asks you what is the light intensity when theta 2 is 30 degree. So here so IF, we call this one IF over I is here. Okay, so after going through the first one, it should be multiplied by 1/2 because originally it's unpolarized. So we have a 1/2 factor. And then between theta 1 and theta 2, and here we have theta 2 to be and here we have a theta 2 to be 30 degree. Okay, so between theta 1 and theta 2, it is a 30 degree, so we multiply it by cosine square of 30 degree. And then between theta 2 and theta 3, there is 60 degree between them, so we need to multiply by cosine square of 60 degree. Or you can regard it as a 90 degree minus 30 degree, like this. Okay, so actually we get the same answer as before, which is a 9.4%. So roughly here, this should be 30 degree. But you feel like this is quite high, but actually this is not the incident intensity. This is the maximum output intensity when theta 2 is 45 degree. So this is as high as 9.4%. So if you're interested, you can try to calculate if cosine square of 40 degree, cosine square of 40 degree. Cosine square of 40 degree is a square root of 2 over 2. So we have to the 4th power. So this one is like 12.5%. 1/8. This is 1/8. This is 9.4%. Okay. So this is the answer to this additional example. And then we have another one. So it says a certain helium neon laser, 氦氖镭射, emits a red light in a narrow band of wavelength centered at 632.8 nanometer with a wavelength width of 0.01 nanometer. What is the corresponding frequency width for the emission? Okay, so actually in this example, we need to use the property of C equals F lambda. C is the speed of light, F is the frequency, lambda is the wavelength. It's the wavelength. Okay, so this question might be strange to you because you may imagine the frequency is a fixed frequency, like E equals Em cosine of kx minus omega t. So this angular frequency, or the frequency omega is actually 2 pi f. So it only consists of a single frequency, but practically it will not be like this case. It will not be like this case. Just say this is cosine, but practically in the world we cannot have a perfect sine wave. So, and maybe suffer from noise. Okay, so the frequency might be radiating. Actually, in circuit design theory, we call it like a jitter. So probably if you need a sine wave, the period might be varying. So it makes it like you have a small frequency range. So actually, I suppose you have not learned the Fourier transform yet, but actually I need to use it anyway. So suppose you have a sine wave, and then you do the Fourier transform. If the frequency is just say fc. Suppose the frequency is fc. So in the frequency domain, you should get a so-called delta function. The delta function in the frequency domain. The delta function means the component is infinity, which is like we will denote it as a delta f minus fc, and delta f minus fc means this is infinity when f is equal to fc, and then delta is 0 and when f is not equal to fc. So it only consists of the component at fc. But in the real world, it won't be like this. It will be like this. This is fc. Even though the frequency component is concentric near the fc, but there are still component which is only close to fc but not actually fc. Okay, so in this way we can define the frequency deviation or the frequency width. So this is so-called the frequency width. And as much as we have frequency width, so we should also have wavelength width. So if you take the reciprocal of the frequency, just say for this point, you take the reciprocal. This point is slightly larger than fc, and then if fc is correspond to lambda, so this point is slightly larger than fc. This is lambda c, and this point will correspond to a point slightly shorter than the lambda c. And then suppose this one, you take the reciprocal. This point is slightly lower than fc, and then you take the reciprocal. It will go to the other side. And then this is something like this, and then you can check it like this. And then we can also define this is the wavelength width. Okay, so actually you can do it like, suppose we have the wavelength center. So this one is equal to 632.8 nanometer, and then the width is 0.01 nanometer. So you can you can assume this point is a 0.328 632.8 plus half of 0.01 nanometer, and then this one is 632.8 minus 0.01 over half, and then you take the reciprocal, not actually the reciprocal, you use this formula to calculate f equals c lambda. So we have a lambda, this one is lambda 2, correspond to f2, and this one is lambda 1, correspond to f1. So lambda 2 minus lambda 1 is actually this wavelength width, and then you can just plug in lambda 1 and lambda 2 to here, and then you can find f1 and f2. But here f1 is larger than f2, so the wavelength width, the frequency width is f1 minus f2. Okay, so this is the physical phenomenon, or the physical interpretation. Actually, we can make use of the calculus to simplify the calculation. And this is actually like, we can write it as f equals c over lambda, and then we can take the differential, we can differential both sides. So we have a df equals d c over lambda, and c is actually a constant, so it is like c times d 1 over lambda, and it's just like taking the derivative, but yeah, we multiply df to the other side. Okay, so we take the differential for 1 over lambda, so which is like 1 over lambda is negative 1 over lambda square, so just take d1 over lambda d lambda, and then we will have a d lambda. Okay, or you can just regard it as a df d lambda. So it will be like d lambda c over lambda, something like this, and then you can see, oh, this is actually c, and then this is lambda to the negative 1 power, so it is negative lambda square in the denominator. So it is like this, and then we can just plug in the number, which is actually or actually we can just take the delta f, take the absolute value, and then take the absolute value. Here we have c over lambda squared d lambda, delta lambda, and then we can just plug in the number. 3 times 10 to the 8th power is the speed of light, and then lambda square, lambda is this one, 632.8 times 10 to negative 9, and then quantity square, and then multiply by this one. Wavelength width is 0.01 times 10 to minus 9. Okay, so this number is 7.49 gigahertz. 7.49 gigahertz. Okay. So yeah, so we finished the original slides for the chapter 33. Oh, and let's have a 10 minutes break.